students, good morning. In the chapter of magnetic material, today we will discuss about the magnetic movement of an electron revolving around the nucleus of an atom. Suppose an electron of charge E is revolving around this nucleus. Here is the nucleus and this is the orbital path of electron. Electron revolves around this positively charged nucleus. Electron has a negative charge. Then when electron revolves around this nucleus, a tiny current loop produces here. Tiny current loop produces, in which this electron orbits or revolves. Because the electron revolving around the positively charged nucleus in a circular orbit. This model is shown in figure. A negatively charged electron revolving in an orbit is equivalent to a tiny current loop. Therefore, the magnetic dipole movement due to this current loop, a magnetic dipole movement develop here because the electron revolves around this nucleus and therefore a tiny current loop produces here and the magnetic dipole produces, because we know that in a current carrying coil, there is a current carrying coil. Then, due to the flow of current, the magnetic dipole produces near the loop. One phase of current carrying coil or loop produces N pole and another phase produces S pole. Same as this type of this, here is also a tiny current loop produces. And therefore, the magnetic movement of this orbiting electron is given by ORB, that is for orbiting electron, is equal to, we know that magnetic movement is equal to current into area of loop. We have already discussed this formula. That is, magnetic movement is equal to current into area. Now, if only a part of magnetic movement of an atom and is referred to a orbital magnetic movement, an electron possesses an intrinsic angular momentum, the spin angular momentum. The spin magnetic dipole moment results from this intrinsic spin. Now, consider an electron moving with constant velocity v. The electron moving with constant velocity v in an orbit around this nucleus. The r is the radius of this circular path in which electrons revolve. V is the velocity of this electron. Then the electron travels a distance 2 pi r, that is circumference of this circle, travels the distance equal to 2 pi r in one oscillation or in time period of t. Therefore, from this we can say the time period of revolving electron is, or we can say the velocity of revolving electron is equal to total distance traveled by the electron, that is the circumference of circle, that is 2 pi r, and the total time taken to cover this distance is t. That is, in time t, the electron complete one circular motion. Therefore, velocity is equal to 2 pi r divided by T. We can say this is equation 1 and this is equation 2. Now, we know that the current associated with this orbiting electron can be given by, we know the current is equal to charge upon time. Therefore, the charge of electron is E and time is T. Therefore, I is equal to E upon T. We know that, but T is equal to 2 pi by omega, and we know the omega is equal to V upon R. Therefore, we can write here 2 pi upon V upon R is equal to 2 pi R upon V. Here, in this case, we have used here omega is equal to V pi R, where omega is the angular velocity of electron, and the relation between angular velocity and linear velocity is given by omega is equal to V upon R, and therefore T is equal to 2 pi by omega. Therefore, put the value of T in this equation. We can say equation number 3. We get I is equal to E upon 2 pi R upon V, and therefore I is equal to EV upon 2 pi R. EV upon 2 pi R. Then put this value of equation 4 in equation 1. We know that M is equal to I into A, and therefore I is equal to EV upon 2 pi R. EV upon 2 pi R into A, where A is the area of this loop, and area of loop is given by the equation pi r square. Therefore, we can cancel here r and pi, and therefore we get 1 by 2 into EV, that is orbital magnetic movement. Orbital magnetic movement is equal to 1 by 2 EVR. 1 by 2 EVR. This EV into R, and 1 by 2 EVR. Therefore, we can say that orbital magnetic movement of revolving electron is M is equal to 1 by 2 EVR. Now, we know the angular momentum is given by the L. Angular momentum is given by L, and L is equal to mvr. Then the angular momentum for the electron revolving around the nucleus is given by L is equal to m in base E, that is the mass of electron, m is the mass of electron, then v is the velocity of electron revolving in circular orbit, and r is the radius of this orbit. Therefore, the orbital magnetic movement can be written by this m is equal to, this equation is EVR divided by 2. Orbital magnetic moment is equal to EVR divided by 2. If we multiply by M and divide by M to this equation, then we can write here E upon and here multiplying and dividing this equation by M, that is mass of electron, then we get then E upon ME. Here MVR is the orbital angular momentum. We can put this value here and therefore we get magnetic or orbital magnetic moment is equal to E upon 2 ME into L. Here, in this case, this equation shows that the orbital magnetic moment is proportional to the angular momentum. Orbital magnetic momentum is proportional to angular momentum. But the electron bears a negative charge. This electron bears a negative charge. The vector quantity, that is magnetic moment, and the angular moment are opposite. Magnetic moment and angular moment are opposite, and therefore this quantity can be written as in vector form. This will be equal to, that is, this negative sign indicates that the magnetic moment and angular moment are opposite to each other. Here in this equation, the quantity E upon 2M is called as the gyromagnetic ratio. The quantity E upon 2M is called gyromagnetic constant or ratio. Gyromagnetic ratio. That is, the gyromagnetic ratio is constant. It is the ratio of charge on electron and twice the mass of electron. This ratio is called as the gyromagnetic ratio or gyromagnetic constant. For electron revolving in circular orbit, the angular momentum is integral multiple of n, integral multiple of h upon 2 pi. That is, angular momentum is equal to integral multiple of h upon 2 pi. And also this angular momentum is equal to mvr, and this can be written as h upon 2 pi. Therefore, put in this value of L in this equation, then we get the magnetic orbital magnetic momentum. M is equal to, here, E upon ME into NH upon 2 pi. That is, we can write here NEH upon 4 pi M that is magnetic momentum or orbital magnetic momentum is given by N E H upon 4 pi m, where N is the number of orbit or principal quantum number. If you consider a hydrogen atom, for first orbit, the magnetic moment of electron can be given by, for hydrogen atom, N is equal to 1, that is electron is revolving in first orbit. Then we can write the magnetic moment of electron is equal to EH upon 4 pi m E for the hydrogen atom. For hydrogen atom. Then same as we can put the value of N is equal to 2, N is equal to 3 and so on, where N is the number of orbit, first orbit, second orbit and third orbit. Therefore, we can put the value of N in this equation for hydrogen atom and we can find the orbital magnetic moment. The quantity EH upon 4 pi m is called Bohr magnitude. This quantity is called Bohr magnitude. EH upon 4 pi m. Bohr magnitude. Bohr magnitude. And the value of Bohr magnitude is 9.274 into 10 raised to minus 24. 9.274 into 10 raised to minus 24. That is, putting the value of these terms, these all terms are constant, that is E is the charge on electron, H is the Planck constant, the value of pi is 3.142 and here M is the mass of electron. Putting these all values we get the EH upon 4 pi m is equal to 9.274 into 10 raised to minus 24 ampere per meter square. The magnetic moment of atom is taken in terms of Bohr magnitude. This is called as the Bohr magnitude, EH upon 4 pi m. Is the magnetic moment of electron revolving around the positively charged nucleus. Okay, thank you.